So just to give you a little bit of background, usually Lichnerovich prizes, they're given at the Poisson conferences. And then, as you know, last year, the Poisson conference got canceled, and then it was rescheduled for this year. And then, unfortunately, it got canceled again because of COVID. And hopefully, we'll have the addition of the physical presence Poisson conference next year. But we thought that there should be an addition of Lichnerovich prizes, which corresponds to the last year conference, or if you want, to this year conference. And that's what we are doing now. And I give the floor to the chair of the outgoing scientific committee, Marco Gualtieri, who himself was one of the first prize winners. And so he will announce the prizes and read citations and tell you about the prize winners of this edition. So Marco, I give you the floor.
Okay, thanks, Anton. Hi, everyone. So let me just keep this brief, but I should explain what the contributions are for the prize winners. So the Andrei Lichnerovich Prize in Poisson Geometry, it was established in 2008. And it's awarded for notable contributions to Poisson geometry. It's given out every 2 years at the Poisson Geometry Conference. And it's given to researchers who completed their doctorates at most 8 years before the conference, the date of the conference. The prize is named, of course, after Andrei Lichnerovich, who lived from 1915 to 1998, whose work was fundamental in establishing Poisson geometry as a branch of mathematics. And it's awarded by a jury composed of the members of the scientific committee and the advisory committee. So the scientific committee has about 6 people on it, and the advisory committee has about 20 people on it, drawn from a wide spectrum of people in the Poisson geometry community. And they make nominations, and then we have a vote. Okay, so this year's winners are Pavel Safranov from the University of Edinburgh, and Xiaomeng Xu from Peking University. So congratulations to them. Let me just explain the reason for the awarding of the prize to these 2 great researchers. Pavel Safranov, first, he completed his PhD in 2014 at the University of Texas under the supervision of David Benzvi. After postdocs at Oxford, Bonn, and Geneva, as well as a lectureship at the University of Zurich, he joined the University of Edinburgh as a lecturer very recently. He's awarded the Andrei Lichnerovich Prize in Poisson geometry for his fundamental contributions in shifted Poisson geometry and in deformation quantization theory. He advanced the understanding of classical notions of symplectic reduction and Poisson-Lie groups within the framework of shifted Poisson geometry. His results about deformation quantization led recently to applications to the Bonahan-Wang conjecture on the Azumaya locus of the Kaufman bracket and to Witten's conjecture on finiteness of Skein modules in quantum topology. I think his work is related to many of the works of people in the Poisson geometry community, and I think that for newcomers, it would be great if they picked one of his papers and read it, and that holds true as well for Xiaomeng Xu. Xiaomeng Xu completed his PhD in 2016 at the University of Geneva under the supervision of Anton. And after a postdoc at MIT, he joined the Peking University as an assistant professor very recently. In his work, Xu constructed explicit Ginzburg-Weinstein linearization maps for Poisson-Lie groups and their quantizations. His results on the relationship between Stokes phenomena, the Yang-Baxter equation, and Frobenius manifolds uncovered deep connections between, on the one hand, the theory of meromorphic ODEs with higher order poles, and on the other hand, the theory of quantum groups. He also used classical integrable systems on Lie-Poisson spaces to study the structure of Stokes matrices, advancing our understanding of Stokes phenomena, the isomonodromic deformations, and other topics. In earlier work, Xu has contributed to the theory of Courant algebroids, string principal bundles, and homotopy Poisson manifolds as objects in higher structure aspects of Poisson geometry. So as you can see, in both these cases, their work spans a great variety of topics within our field. And I really encourage, especially young researchers, to pick one of their papers, the one that looks most interesting to you, and to give it a read. Okay, so congratulations to both. Let's give them all a round of applause. I hope that they are here.
I believe they are.
Xiaomeng?
Pavel is definitely here, but there's Xiaomeng.
I'm here.
Is here as well. So congratulations to both of you.
Yeah, congratulations. So thank you, everybody. Thank you, Marco. And of course, thank you, prize winners, for your great work. So we pass to today's talk. Francesco, would you like to share screen?
Yes, hi, Anton. Share screen. Does it work?
Yes, it does.
Okay.
All right. So today we have a great pleasure to have Francesco Bonechi speaking on bi-Hamiltonian systems and invariant polynomials. Francesco, I give you the floor.
Okay. So thank you very much for the invitation, the opportunity to give this talk. Okay, let me check. How much time do I have, more or less?
Usually it is 60 minutes. Of course, we are kind of flexible. Sometimes some of the talks, I think, were longer, but usually 60 minutes is a kind of good timing.
Okay, it will be enough, definitely. Okay, so thank you very much for the invitation, opportunity to give this talk. So this talk is about an activity that I'm doing together with these collaborators, Nicola Ciccoli, Gian Chiu, Marco Tarlini, Emanuele Viviani, which is a PhD student who joined this activity since a couple of years. And okay, so what is this activity? We are studying since some years a class of integrable models on compact Hermitian symmetric spaces. In terms of this example of Hamiltonian geometry, which is Poisson 9-Hoist geometry. So Poisson 9-Hoist geometry is a kind of Hamiltonian geometry that that gives a very geometrical approach to integrable models, and we study a class of them on these compact Hermitian symmetric spaces. Our motivation, this is the reason we arrived to this problem and we try to understand it, is related to quantization of the symplectic groupoid of, let's say, the second of the Poisson structure involved in this Hamiltonian geometry. And so I will try to give, well, the plan of the talk is this. First of all, I want to remind, well, to present the problem and to remind the basic facts about this Poisson 9-Hoist geometry as they were established in the 80s by Magri and Morosi. So very old stuff. But then in the second part, just to give the motivation to communicate what is our point of view to the problem, I will discuss how this geometry, this Poisson 9-Hoist geometry, lived to the symplectic groupoid. And so we lift the integral model and get an integral model on the symplectic groupoid that is in some sense compatible with the groupoid structure. And this is what we refer to as multiplicative integrability. And then in the third part, I will try to give some details of how we understand these models at least in the ABCD cases. We thought to be able to master the general case, including the exceptional cases, but so far we properly understood only the ABCD cases. So in the third part, I will give some details of this construction. Okay, so second and third part are in some sense independent. Second part is more to give a motivation. I will just refer very, very quickly to the quantization problem. And third part, I will give the details of the construction. So what is the problem? Okay, you take some compact semi-simple D group K. You take some coadjoint orbit. So on this conjoint orbit, you have the constant Fourier symplectic form, but you also have the Poisson structure that I call Brouwer-Poisson structure, which is a Poisson structure that comes from the standard Poisson-Lie structure on K. And then the isotropic, you can obtain the coadjoint orbit as a quotient by some subgroup. This subgroup can be chosen in such a way that is a Poisson subgroup of the Poisson-Lie structure on K. So on the quotient, you can define a quotient Poisson structure, and I call this Brouwer-Poisson structure. So you have two Poisson structure, the inverse of the symplectic form and the Brouwer-Poisson structure. And then there is this old result by Koronsky, Radul, and Rubtsov that says that these two structures are compatible if only if this coadjoint orbit is a compact Hermitian symmetric space. Compatible means, of course, that the Schouten bracket of the two Poisson structure is 0. Another way to say that there is a pencil of Poisson structure obtained by taking any linear combination of the two Poisson structure. Okay, so this is an instance of bi-Hamiltonian geometry. Okay. So in particular, it's a way to introduce Poisson 9-Hoy structures. So what you can do, if you have this compatibility between pi and omega minus 1, then you can define this tensor, which is pi is composed with omega, which is a tensor, a 1-1 tensor from tangent to tangent. And as a consequence of this compatibility, this is vanishing 9-Hoy torsion, T of n. This T of n is what this is the definition of the torsion. Okay, this vanishing of torsion tells us that this is a Poisson 9-Hoy manifold, not the most general one, because this is of symplectic type. In general, you can take instead of omega minus 1 a general Poisson tensor. But,
Francesco?
Yes?
Just a naive question. In this case, right, we know very well the KKS structure, and we know maybe less well, but still the Brouwer-Poisson structure. But yes. Now, if you start the iteration, say for instance P2, do we know what is it, or like is it something reasonable? Is it studied by someone?
I don't think they are studied. No, not to my knowledge. These are definitely not studied structure. You mean the Poisson structure of the hierarchy? No, I don't think they're much studied.
For instance, the simplest example, is it like a two-sphere?
Two-sphere, exactly.
And then on a two-sphere, I can imagine, just by chance, did you check what are those P?
Well, I think in the case of the two-sphere, you see the Brouwer-Poisson structure is simply so if you express it in complex coordinate in the stereographic projection, is simply the del bar multiplied by 1 plus z squared. And I think if you go on, you take power of this factor.
So 1 plus z squared will be to some whatever.
To some power, I think.
Mm-hmm.
I think so.
So it will be then probably what, vanishing more and more in
yes, with more degenerate in the infinity. This is what I expect. Yes.
Okay. Thank you.
But in general, it's not studied, and I have to say that many of these things go for every Poisson. Many of the things that I will say will go for any Poisson structure of the hierarchy. So in principle, this could be interesting to study also the other structure. And well, one can also expect that they are different in nature, right? As in the same way they are different. The first two, right? One is symplectic, the other is not. So maybe it's interesting, but I don't know. Actually, I don't know anything about that. Okay, so as Anton was saying, there are many consequences of this fact, but one is exactly the one Anton was referring to, that you can compose the first Poisson structure, which is omega minus 1, with powers of the 9-Hoist tensor. And what you get, it's a family, an infinite family of compatible Poisson structure. So this Pj, which is n to the j, applied to omega minus 1, is a Poisson structure, and Pj and Pk are compatible. Okay, the basic object that we are interested in is this notion of Hamiltonian forms. Hamiltonian forms are what? This is the definition take. These are closed forms, but such that also when they are closed also after you apply the 9-Hoist tensor on that. So they have a lot of properties. For instance, they define a Lie algebra with respect to the bracket defined by every Poisson tensor of the hierarchy. So every Poisson tensor defines a bracket on one forms, and so you can use this bracket and do the bracket between two Hamiltonian forms, and this is still an Hamiltonian form. And they are closed under the action of n. Okay, so if you take an Hamiltonian form, df, okay, we imagine to work with some manifold which is simply connected. So Hamiltonian form are exact. So we take an Hamiltonian form df, we apply n df. This is still closed and is still exact. So for every Hamiltonian form, we write a relation like this, that n df is dg. Okay, and so this means that these Hamiltonian forms comes in hierarchy, because you can go on, apply to the first df powers of n, and then you will get new df of k. This gives this a hierarchy of forms or functions that we call a linear hierarchy, all satisfying this property, this relation, and dfk is equal to dfk plus 1. Of course, all these one forms commute with respect to the Koszul bracket of every structure in the hierarchy. There is one hierarchy we are particularly interested in, which is the trace of the powers of the 9-Hoist tensor, because they satisfy, they define exactly one hierarchy. So in particular, they define Hamiltonian forms. In particular, this implies that these functions ik are in involution with respect to all the Poisson tensor in the hierarchy. So I will refer to this as the canonical hierarchy, linear hierarchy, and this is the one we are interested in, because this is canonically defined in our geometry. There is another very simple fact that I want to mention, is that you take any Hamiltonian form, and then it's very easy to realize that this, if you apply the inverse of the symplectic form, so the first Poisson structure in the hierarchy, you get a vector field, and this vector field is closed under the Lichnowitz differential of the second Poisson Poisson structure. So omega minus 1 alpha is a Poisson vector field for pi for every Hamiltonian form. So in particular, if you take the Hamiltonian appearing in a linear hierarchy, they satisfy the relation and the fk is equal to d fk plus 1, which means that pi dk is equal to omega minus 1 dfk plus 1. Okay, so this means what? That the Poisson vector field associated to the hierarchy is Hamiltonian for pi for every function of the linear hierarchy apart the first one. Okay. Sorry.
No, I think it just fine. Continues. If someone wants to ask a question, they will do it. Okay.
So the statement is this one, that all these Poisson vector fields are Hamiltonian apart the first one. The first one can be non-Hamiltonian. Okay. It's just Poisson. Okay, in particular, we can consider the canonical hierarchy and take the lowest one, which is I1, the trace of n, and you take the Poisson vector field of this I1. This is proven to be the modular vector field of the Poisson structure pi with respect to the symplectic volume. Okay. So
Francesco?
Yes.
I'm just slightly confused to the modular vector field, but it is right. But for a symplectic case, the modular class is 0, right? So
it's the modular vector field. You know, with respect to the symplectic volume, that means that in order to define the modular vector field, you have to choose a volume form, right? But it's a modular vector field. I forgot to write it with respect of pi of the second Poisson tensor.
Oh, the second one. Oh, I see.
Choosing as a volume form the symplectic volume form.
What about modular vector fields for higher ones? Can you also produce them in that way, or?
Well, this I don't know.
Okay.
This I don't know, but definitely it's a good question.
Okay, thank you.
Well, definitely you can do it, because if you start, no, I'm not sure. Well, it's interesting, but I don't know the answer. Okay, but let's say what is peculiar here is that the first Poisson structure is symplectic, so you have a volume form. If you go to another step on, and you will compare the third with the second does not define a volume form. So I don't know if it's reasonable to expect that you can have the same interpretation going on, but okay, you can think of it.
But for this part of the discussion, is it important that you are still on the quadrant orbit?
No. Sorry, this is complete. I'm repeating basic facts of established in the 80s general for this Poisson line-Hoist geometry. So this is completely general.
Well, so you can iterate this. Okay, good. Thank you.
No, of course you can iterate, but if you iterate, you can take you can start with P1, right? And then you have again a Poisson line-Hoist structure, but this P1 is not anymore symplectic, right? So the statement cannot be the same, right? Because you don't, the symplectic form here, you need it for define the symplectic volume. So I don't know what should be the replacement for the statement, but maybe there is, I don't know. Okay, so of course we are interested in this integrable model given by this canonical hierarchy, but of course we don't know if this canonical hierarchy gives independent functions. So this is, we know only that they commute, but could be independent. So we have to assume this, and then this is an assumption that we can state like this. So what you can say in general that distinct eigenvalues of this tensor n, I didn't write it n, but so distinct eigenvalues of n can be pointwise at most 1/2 the dimension. Of course, here I say dimension of O, but whatever it is, this is complete. These facts are completely general, not only for the coadjoint orbit, of course. So we assume that these distinct eigenvalues are exactly 1/2 the dimension, so they are maximal almost everywhere. So in this case, I state this by saying that this n has maximal rank. So if this n has maximal rank, this is a statement of independence of this function, and then the model really, it's an integrable model. You can prove that you can define eigenvalue functions, so functions that pointwise give eigenvalues, and then they satisfy this equation that n applied to the d of lambda is equal to lambda d lambda. So this form is completely general. And Hamiltonian, the Lie algebra of Hamiltonian one form is abelian for all the bracket appearing in the hierarchy. And this eigenvalue function gives a system of action variables, okay? Of course, these eigenvalue functions, they are defined even if we are in maximal rank, they are defined only on a dense open set. And there is no guarantee in general. It's not true that they are global smooth functions. In the examples that I'm going to discuss, they typically extend to they become a global continuous function. So there is some singularity of the derivative, and this, for instance, in the kind of direction that we are thinking of, plays some role.
Francesco?
Yes.
Just when you say they're action variables, does it mean that they generate circle actions?
Well, not, of course. You don't know. Typically, yes, but not everywhere. So you
not everywhere, but generically they have
yes,
period, the same period, right? They generate orbits with the same period, or what?
Yes.
Or not? Because I mean, they Poisson commute, that I understand, but typically when we say action variables, this means that when you generate a flow, this should be a circle action with the fixed period. Is it the case?
Yeah, I think so. Yes, I think you can define angle variables.
No, wait. You're saying those eigenvalues are action variables. So you don't need to do anything else, or is it just to understand?
No. Well, I would say yes, but I'm not. I'm not completely sure that this is true.
Okay.
Probably I'm ignorant about this.
Okay, thank you.
Yeah. Okay, so let me go to the second part. So the basic fact is this that I want to discuss is that this kind of geometry can be lifted to the symplectic groupoid. Okay, so I'm going to discuss this, what we can lift, how we can lift these things to the symplectic groupoid. A symplectic 9-Heuss groupoid is a symplectic groupoid, G over M, and omega G is a symplectic form, equipped with a multiplicative 9-Heuss tensor. So it's a 1-1 tensor on the groupoid, and such that this gives a Poisson 9-Heuss structure on the groupoid. So multiplicative tensor means that it's a groupoid homomorphism between the tangent groupoid. So the tangent groupoid is a groupoid, and G is a groupoid morphism. Okay, this is the meaning of multiplicative. And in this paper by Tianone Ping Xu, it is proven that the unit space of symplectic 9-Hoist groupoid inherits a Poisson 9-Hoist structure, and every integrable Poisson 9-Hoist structure is the unit space of a symplectic 9-Hoist groupoid. Okay, so if you assume that your Poisson 9-Hoist structure is integrable, well, I mean, the Poisson structure appearing in the Poisson 9-Hoist structure is integrable, then you can lift the 9-Hoist structure to the groupoid in such a way that the 9-Hoist tensor is multiplicative. So one can do it for every Poisson groupoid, for the symplectic groupoid of every Poisson structure in the hierarchy. And then you can study Hamiltonian forms of this Poisson 9-Hoist structure exactly in the same way I was discussing before. But it's interesting to see that you can lift the linear hierarchies of the Poisson 9-Hoist structure on the base, and lift it to become linear hierarchies of the Poisson 9-Hoist structure on the groupoid. So this is very, very simple. So suppose that you have this linear hierarchy. So this function satisfying this condition, and dfk is equal to dfk plus 1. Of course, this n is a groupoid it's a groupoid morphism. So you can exchange, you can apply this you can apply to this relation the pullback of source or target map, and then it commutes with n, and then you get this relation working on the groupoid. Okay, if you apply this, which is L is the, let's say, source map. Okay, but then you have another way to lift this linear hierarchy to the groupoid. Remember that I told you that every you take any function in the hierarchy and you consider the Hamiltonian function, the Hamiltonian vector field with respect to the symplectic structure. And then, well, remember that this is what I told you, that this is a Poisson vector field for the Poisson structure pi, which, by the way, is Hamiltonian also for pi for all k bigger than 1. Okay, but then for each of these Poisson vector field, you can consider the groupoid 1 cocycles that integrate this Poisson vector field. Okay, so every Poisson vector field can be integrated to a groupoid 1 cocycle, and then you prove that. So these groupoid 1 cocycle are function over the groupoid. So you can apply the 9-Hoist tensor on this on the differential of this 1 cocycle, and you prove that they satisfy this relation. Okay, so again, this function defines a linear hierarchy on the groupoid, where the first one is h of f1, the groupoid cocycle associated to the f1, and the higher ones are h of f2, but h of f2 is delta star of f1, where delta star is the coboundary differential of the groupoid cohomology. Okay, because all the higher vector fields are Hamiltonian. The lowest one, no. So the first one is just the groupoid cocycle, and the other one are the exact groupoid cocycles. So you see, every linear hierarchy can be on the unit space can be lifted to become two two linear hierarchies in the groupoid. So it's quite easy to check that if you have n of maximal rank down, then you have a n of maximal rank even up, and so you have an integrable model on the groupoid. Okay. And we call this a multiplicative integrable model because it's an integrable model in the ordinary sense of symplectic geometry, but it also has a degree of compatibility with the groupoid structure. So in particular, I told you that the first Hamiltonian of the canonical hierarchy, and if you take the Hamiltonian vector field associated to this first Hamiltonian, which is trace of n with respect to the symplectic form, it's the modular vector field of the second Poisson structure, and so what we lift to the symplectic groupoid is the modular function, so the cocycle corresponding to the modular vector field. So this kind of integrable model, it's an integrable model that contains among the Hamiltonian in involution the modular function. So for this reason, we refer to this problem as a multiplicative integrability of the modular function. So let me mention very, very briefly what was our motivation to do all this story. I will be very sketchy because this is not what I'm planning to discuss, but just to complete the landscape. Our idea was to use this integrable model as a real polarization for the symplectic groupoid. And use why we want to do this, because you can prove you can prove this, that if you define the contour level set of this Hamiltonian in involution, and then you go to the quotient, this define a quotient from the groupoid to the space L that I call L of n, the space of these levels, and this space inherits the structure of topological groupoid. So the kind of compatibility that this Hamiltonian have with the groupoid structure allows to say that if you fix the contour level, and then the set of values of this contour level it becomes a topological groupoid. Okay. And so the idea would be, okay, to use this as a sort of polarization. Of course, it's a very, very singular polarization in general that does not allow you to do any geometrical quantization. But still, since there is this additional groupoid structure, you can use it in some way. So we worked out this program only for one example, which is complex projective spaces, where more or less it works like this. Of course, this case is very good because the integral model is quite simple because it's just a toric structure of CPN. So the eigenvalues are globally smooth, and then they define smooth Poisson vector fields that give rise to groupoid one cocycles, which are a smooth function over the groupoid that are called HI. So lambda I are these eigenvalues, HI are the cocycles integrated to the groupoid. And then this couple lambda H gives a set of global coordinates that allow to define this, to describe this topological groupoid. And you can get a very explicit description in this case because you can describe it as a subgroupoid of an action groupoid where one Rn, which is the space of H, acts on the space of lambda with a multiplicative, just by multiplication, in a multiplicative way. And then you restricted this action groupoid to, sorry, this delta here should be Rn and then restricted to delta. This is a mistake. So you take the action groupoid and then you restrict to delta, which is just the image of the eigenvalues lambda. Okay, in this case of CPN would be just the sum polytope of CPN. And then once you have this description, which is quite explicit, and you know a lot of things on this integrable model, you can compute the groupoid of Bohr-Sommerfeld leaves, and then define out of it the convolution algebra that you regard as an output of your quantization procedure. It works for CPN, and it works, of course, because the integrable model of CPN is very simple, and has all these properties. But in the general case, of course, we don't know much. We need some information of the integrable models. In general, these eigenvalues are just are not global. They have singularities in the derivatives, so we cannot define Poisson vector field, and so we cannot lead to cocycle and so on. We have to find some different description. Okay, so for this reason, we said, okay, we must understand a little bit better this integrable model for the general case. So let me, so I'm going to the last part of my talk, and then I try to describe how we try to understand this integrable model for the general case, for the general emissions symmetric, compact emission symmetric space. Okay, so let me fix some notation. So for us, K is a compact simple Lie algebra. We fix some Cartan subalgebra, fix some positive roots. These positive roots will fix this operation that I call J, which is just a complex structure in the space of the root vectors, which say that two positive root vector multiplied by I, negative root vector multiplied by minus I, and then 0 on the Cartan. And so we say that our orbit is an orbit of a certain element that called rho phi. Rho phi is an element of the Cartan, and I call K phi the subgroup that commute with rho phi. And in general, the Lie algebra, this subgroup has this structure. It's just a direct sum of semi-simple Lie algebra, K prime, plus a one-dimensional center that is generated by this rho phi. So what else do we need to recall? That this rho phi, this phi refers to the unique simple root, such that E phi, the root vector associated to that simple root, does not live in the subalgebra, in the complexified subalgebra. Okay, so this phi, I will refer to this phi as a non-compact root. Okay, so this every symmetric space comes with the choice of a non-compact root of the Lie algebra. Okay, and this rho phi is normalized in this way, such that rho phi over phi is I. So this means that the automorphism that defines the symmetric space is this e pi to the rho phi, is such that the square of the adjoint action of this automorphism K phi is 1. Okay, so I realized that this K phi, I use the same notation for K phi, which is an element of the group and the full group, which is not a good idea, but this here is just an element of the group, and this here is the group. Okay. So this is all I need to know about these spaces. Okay, so we have an integrable model on these spaces, and okay, there is a very old.
Sorry, just maybe a stupid question. If you go on the previous slide, so how is it? This rho phi, is it an element which in the end will define for you a complex conjugation, right? Or like is it so?
This rho phi is the one that define this automorphism K phi.
Mm-hmm.
And this split the Lie algebra into the eigenvalues 1 and -1. Mm-hmm. So okay. K phi is the eigenvalues 1, the eigenspace of eigenvalues 1, and then K phi perp. So it's orthogonal with respect to the the inner product is to invariant inner product to K phi. So
but that's the complex structure, right? The thing which squares to -1, right?
Ah, yes. This yes, this J really gives the complex structure.
Yeah. Okay. Yeah. Thank you.
Okay, so what we are doing is trying to, if you want to recognize we know that there is some integrable model in these spaces, and we want to recognize what we want to describe it, to understand what it is. Okay, so the idea is to use an old method to construct integrable models on Hamiltonian space, which is a T method for defining commuting Hamiltonians. Okay, and we think that this is our candidate should be of this form. Okay, this is our guess. So what is first of all, this T method? T method is very, very simple idea. So you take an Hamiltonian K Hamiltonian space O. You take the moment map mu, which is okay, mu with values in K star, and then you take two subalgebra, Ki and Kj, nested subalgebra. So you will have a moment map for Chi A and Chi J, which is just composition of the full moment map with projection to the dual. And then you take two invariant polynomials, one for Ka and one P for its invariant polynomial of Ka, Q is invariant polynomial for Kj, and you pull back with the respective moment maps to the Hamiltonian space, and then you compute the bracket. Of course, well, you can write the second moment map by using this decomposition, and you can put outside the moment map of the bigger subalgebra Ka. You use the fact that this is a Poisson morphism, this goes out, and then you have to compute the bracket in the dual of the Lie algebra. But in the dual of the Lie algebra, P is a Casimir, okay, so this bracket is 0. So this tells you that if you take a chain of nested subalgebra, like the one that I wrote here, then all invariant polynomials of each of these subalgebra will be in involution, okay, just for this simple observation. And this every chain of subalgebra define an algebra of involutive Hamiltonians. Okay, of course, integrability means also to be sure that these are independent, and this is, of course, the tricky part, and it relates to this idea of multiplicity free of the action of the groups on the Hamiltonian space, but this is not something that I want to discuss now. Okay, my problem is that, okay, this is very nice for omega. What about pi? What happens if I do I compute the Poisson bracket with respect to the second Poisson structure? Okay. And so Of course, if we take a generic chain of subalgebra, we don't have any way to discuss this problem. So let us start by imposing certain condition on this chain of subalgebra. So the condition that we want to impose is this. You take the perpendicular of each of these subalgebra, K-perp, and make the hypothesis this J leaves this perpendicular invariant. Okay, so this is the first condition that we require. Second condition is that, of course, Ki, adjoint action of Ki leaves Ki perp invariant. So you have two linear operators on K perp, and you ask that J commutes with the adjoint action of X for every X in Ki. So these are two hypotheses that two requirements that we ask to the chain of subalgebras. Okay, without knowing anything more, you can compute the following formulas, which is this one. You take every invariant polynomial P of the subalgebra Ki, and then you compute ND of P. Okay, and then you obtain this formula, which is this one. Of course, this formula is based on the form of the Brouwer-Poisson structure. So I didn't write any formula. So well, this formula in particular doesn't mean anything. But just to understand what kind of things that we obtain. So NdP is equal to D of P plus this element where I denote with P tilde the multilinear functional that you associate to an invariant polynomial. Take an invariant polynomial of degree homogeneous of degree R, then you will get P tilde as R linear invariant functional, okay, on Ki. And so you evaluate this P tilde on this on the moment map. So, but in one entry, you evaluate on the differential of this element of AK. Okay, what is AK? AK is this element here, which is done like this. So you take the moment map, you take the component along K perp, you apply J to this. It's another element in K perp. Do the bracket. And then you obtain something that in general will live in K, but you project on Ki. Okay, so this is an element which lives in the subalgebra. Of course, it's a function with values in the subalgebra. Okay, what is good of this formula, which probably doesn't sound particularly meaningful to you, is the fact that all this property depend on this element A. Whatever is P, okay, we have to study this element A for each subalgebra. And of course, what we are trying to prove is to prove that this NdP is still an invariant polynomial. So it's a differential, well, it's generated by invariant polynomial, right? And so what we have to do in order to establish this property is to study this element for each Ki. Well, this formula is just, let's say, result of explicit computation. It's nothing more, but still it's a good form for us. So what you can get from this formula, you can get that NdP is a K invariant one form, okay? And then you can get also that if you take two invariant polynomials P and Q, and you do but with respect to the same subalgebra Ki, you compute the bracket with respect to pi, well, I didn't write z equal to 0. This is equal to 0, sorry. So it's they commute, but a polynomial of the same subalgebra. Okay, so it's not still the result that we wanted, because we want to take P and Q for different subalgebras. Okay, but for P and Q of the same subalgebra, this is a kind of hypothesis that we did on the chain of subalgebra is enough. Okay, so we have to understand about what can we say if you take P and Q of different subalgebras, Ki and Kj. Of course, this is where our general procedure needs to, it is not anymore completely general, right? Because we have to discuss sufficient condition for this. And one sufficient condition is this one. If this A that I defined here, this element here, is commutes with the moment map. If this is true, you get whatever you want. You find that NDP is also basic, so it's basic, and then you also find that P and Q commute if P and Q live into different subalgebra. So invariant polynomial for two different subalgebras. So this condition is good, but it's just a sufficient condition. In particular, if you have this, you can prove that together with multiplicity freeness, this implies that invariant polynomials are left invariant by the application of ND. Okay, so let us see when this condition is satisfied. Okay. At this point, we can decide what is, make a guess of what is our chain of subalgebras. Okay, so we can define very general form the chain of subalgebra in this way. Okay, let us start with some non-compact positive root phi 1 of K, which can be the same that defines the symmetric space, but even or can be different. In the case of SUN, it will be different. The other case will be the same. Okay, so we fix a non-compact positive root. This defines the subalgebra, which is in the way I wrote before. It will be K prime simple plus a one-dimensional center, and then we go on. We take a non-compact positive root phi 2 of K prime, and then we define K2 in this way. Okay, phi 2 will define a subalgebra K phi 2 of K prime phi 1, and then with this we define K2, and then we go on. Choosing at each step a non-compact positive root, we find a chain of subalgebras. I just listed these choices in not all cases, but almost. Of course, these choices it's almost unique, not always unique. Typically, when you go to SO, SO even you can have two choices. You can have one choices that gives us a subgroup SO n minus 2, or you can have a choice that gives UN. Okay, but in the other case, this fixes uniquely the chain. Okay, the point is that in order to analyze the problem, we need to choose also a representation of the subalgebra, which has certain properties. So what is this representation? Suppose that I choose a representation on V of K of the full algebra. Okay, this representation splits into representation of K phi, where phi is a non-compact root of the subalgebra associated to the non-compact root phi. What are these representations? These representations are just correspond to the two eigenvalues of the exponential 2 pi rho phi. Okay, sorry, exponential of pi rho phi. The exponential of 2 pi rho phi must be, since the adjoint action of this element is square to 1. This element must be proportional to identity. So a pi to the rho phi should have only two eigenvalues, okay? And so these are the two eigenspaces V plus and V minus. Of course, these V plus and V minus are representation for the subgroup. So this is the composition representation of the subgroup, but it's not obvious that they are irreducible, okay? So in general, they are not irreducible. So we look for some representation V such that one of the two that I call V plus is reducible, but in both representation V plus and V minus, rho phi is constant, is proportional to identity. Okay, this would be assured if they would be irreducible, but since in general they are not, it's a requirement. Okay, so we look for a representation such that in this decomposition plus B minus, the center of the subalgebra in each of the sub-representation is proportional to the identity. Just to give a name and refer to this, I say that this representation V is phi decomposable. Okay, so what's the point of this representation? It's a very technical point, but at least this I want to tell you. So suppose that we have this representation, okay, and suppose that phi is exactly the non-compact root that defines the coadjoint orbit k over k phi. So the moment map is the adjoint of this rho phi. Once that I identify G with K star. So I can take this moment map in the representation rho. And since this rho phi has two eigenvalues, this moment map satisfies a quadratic relation. Okay, it's just a minimal polynomial of this matrix. Okay, which is this one in blue. This AV is just A plus, the one corresponding to the irreducible part. Okay, I put it here. So this quadratic relation is a relation that to us is the key to solve the problem. Without this, we are not able to solve it. So we have to require that it exists this representation. Okay, I can go on. This representation must have also other properties that are satisfied. Let me simply, I skip these details because really these are details, but what is very important that you can go on and reducing, we have this chain of subalgebras. So at the first step, let us suppose that phi is equal to phi 1, okay? At the first step, we decompose V into V plus V minus. Then V plus, it's a representation for K1. But then K1 is again given by a non-compact root, so we want that V1 decomposes V1 plus decomposes as sorry, it doesn't work very well my pointer. Okay, V1 decomposes at V2 plus V2 minus and so on. We go on. This decomposition can go on, and at the step J we will have a decomposition of the full space into two spaces, which are representation for the subalgebra Kj, and with these choices, the perpendicular part of the moment map can be written like this, with a 0 here, and these two terms nu that contributed to the computation of AK. I recall that AK is this element that we have to understand how it works. So if you put everything together, you put the quadratic relation, these properties of the moment map, you can prove that AK is written in terms of the moment map of the subgroup in this way. Of course, this is a direct consequence of the quadratic relation, okay? And so in particular, it commutes with mu. It's just a polynomial in mu, so it commutes with mu. And we can give also a very explicit expression to the action of the Nine-Hoist tensor. For instance, we can take as invariant polynomial the trace of x in this representation, the representation that appears in this decomposition here, so the one appearing here in the 1-1 element of the matrix, okay? And put this expression for a k, which is in terms of the moment map, and we find this very simple relation, okay? This very simple relation on the invariant polynomial. So in this way, you prove that invariant polynomials are left invariant by the action on ND, and you find this very simple relation. You can very easily extract the eigenvalues, which will be the eigenvalues of n, which will be the eigenvalues of the Bowman map in that representation. And so the problem is very easily understood. The role of this decomposable representation in this construction is to give a good basis for invariant polynomial, okay? But of course, if it is true for this basis, will be true for invariant polynomials in every other basis. The formula will be more complicated, but the fact that n lives invariant, the invariant polynomial of the subalgebra is still true, okay? So it looks more than some trick than an essential point. So the only point is that does this representation exist? Well, in all classical case, this representation exists. And well, in the SUN case, you just take the fundamental representation, is decomposable with respect to every non-compact root. The only case where you have to do something which is a little bit more exotic is the SO case, where you have to take the spin representation. And if you are interested to the symmetric space SO divided by the SO, okay? And the other case, you take the fundamental representation for SP and the vector representation for SO if you are interested in SO divided by UN. When you go to exceptional case, this representation does not exist. There's no representation like this, the minimal situation that it decomposes in three representations. If you want the decomposition in irreducible representation. So, well, well, we were much more optimistic because we thought that this method should work in the general case, and the exceptional case behaves in a different way. And it's not clear, I have to be sincere, it's not clear if it is just a technical complication of, or really there is some behavior which is completely different in the exceptional case with respect to the ABCD case. So far we have only partial results, so I don't think it's worth discussing them. So this is our next problem to really understand this case. Of course, we did this to lift the problem to the symplectic groupoid. So what we at the very end, we are really interested to understand what happens to these invariant polynomials when they go up to the symplectic groupoid. Of course, our long-term goal is to understand from this very peculiar point of view something of these quantum symmetric spaces that have been studied in the theory of quantum groups. And of course, we hope to be able to see some something of what has been described in that world. But this is just a very long-term goal. So thank you. This is what I wanted to say.
Thank you, Francesco. So any questions or comments? Yeah, you can mute yourself, or you can raise your electronic hand, or I got perhaps a somewhat naive question. So, so at some point you mentioned those action variables, and typically we expect action variables for such a compact integrable system to take values in some polytope. Do you know something about the polytopes?
Yes. Well, in the case of SUN, this is just a Gelfand cycling system. Okay. So this I didn't say, but this is in the Gelfand cycling. Well, in the SUN case, this is Gelfand cycling system. So these polytopes are exactly the Gelfand cycling polytopes. In the other cases, they can be described. We did it, but well, at least for us, there were new cases, so we have to really to give some description of these polytopes.
So in some way you have an explicit set of inequalities, or what's your description of polytopes?
Well, in the Gelfand cycling is the usual one. In the other cases, you have other sets of inequalities.
But like for SP?
Yes, we have it. We have it. We have it. But let me see if we wrote it actually in one paper. But at the moment, I cannot tell you how is it.
Yeah, no, okay, but just so
I cannot give you the description here, but we have it. Yes, we have it in the paper, in one paper that we wrote.
Okay, very good. Any other questions or comments?
Hi, I have a question. Hi, Francesco.
Hi, Alejandro.
I wanted to ask you about this part about quantization. Do you know if you can define a quantization map from functions on M into this convolution algebra?
No, this is
using
exactly
Fourier transform.
Okay. This is exactly what you don't have. Okay? So in general, of course, the kind of quantization that you get is simply a convolution algebra. Okay, and you don't have a quantization map. Of course, it's exactly the same problem of geometric quantization. You select a polarization, and then there are certain Hamiltonian, the one who are compatible with the polarization, that you get an explicit geometric quantization gives you an explicit operator. Okay, but for those Hamiltonians which are not compatible, you don't have. In general, of course, you can invent methods to do it, but of course methods are limited to certain situations. So it's exactly this. You will have for certain. We are quantizing an integrable model, right? So you know very well what happens to the Hamiltonian that are in involution. Okay, but for the general Hamiltonian, no, of course.
I see, but the system is on the groupoid, and you could, I mean, some of the functions come from M, right? So which are the functions that you, in the end, you quantize?
Well, those who are able to quantize very easily are all the function of lambda. Okay, if you want to think to the function over the unit space, the one you are interested in, because you want to see this as a problem of quantization of the Poisson manifold, which lives in the unit space. So this is a method that gives a quantization of the function of lambda, right? The other one, well, you have to invent a method, but from this point of view, well, it's the same kind of problem that you have in general geometric quantization, because in general geometric quantization, you know what to do with the function, with observable which are compatible with the polarization.
I see. Okay, thank you.
Thank you. More questions or comments?
Can I ask a question?
Sure.
Hi, thanks for your talk. It's really great. So you mentioned near the beginning, I mean, the reason that you're focusing on this particular class of examples is because of this theorem of Koroshkin-Radul-Rupsov.
Yes.
Where you have a symplectic type Poisson-Neuenhaus structure, right?
Yes.
And they say that it's for compact Hermitian symmetric spaces.
Yeah.
Is there another kind of class like this? Is there another source of examples where one should look for a similar structure?
Well, in their case, well, in their paper, they prove it also for non-compact, Hermitian symmetric spaces. So this compatibility is true also for the class, for, let's say, every compact symmetric space has a dual, let's say, non-compact. So it's true also for the dual non-compact. So this is for sure. You can apply the same to them.
Ah, so you say that even for the non-compact ones,
Yes,
the same thing should hold. So
the same results also for the non-compact. Yes.
is that did you study that case in your paper also?
No, we focused only on the compact case.
What do you think could be the relation? I mean, is it expected that the quantizations should be somehow related for the duals?
Well, to be honest, I would expect it, but it's a very naive guess. I don't know. I don't know. I think so. I think a good guide for this to understand what happens really to go in the literature on quantum groups, because these spaces are semi-classical limits of these quantum symmetric spaces which have been studied in the literature of quantum groups.
Okay.
And I think, well, this is what I plan to do. We are going very slowly in these things, but this is something that I plan to do just to understand a little bit the literature. Of course, the world is completely different, but I think they can give you some idea, I think, of what you should expect to happen.
Okay, thanks.
Thank you. More questions or comments? I've got one more naive question where maybe I missed some things in the beginning of the talk. So suppose you have this hierarchy of Poisson structures, and you're saying like maybe the zeroth one or the first one is symplectic, but then what about the other ones? Do we know that they admit symplectic groupoids? Is there any relation between eventually symplectic groupoids corresponding to different structures in the hierarchy? Does it because you were discussing what happens with the functions or with cocycles, but what would the other ones also integrate to some other symplectic groupoids?
Well, this is the answer again is I don't know. It's something that I wondered if you can say something about the relation of the symplectic groupoid appearing in the hierarchy. But to my understanding, there is nothing easy. Well, of course, you can ask this question in the first step: what is the relation between the symplectic groupoid of the symplectic structure and of the Poisson structure? Apparently, I wouldn't say, I don't know what it is, right? So I don't know. I think it's an interesting question. I tried even to think of it a little bit, but I don't have any answer. So I don't know if they are integrable. If you can say that they're integrable, I don't know anything about this.
Okay, thank you. But we were not supposed to necessarily ask easy questions, right? We were just supposed to ask hopefully interesting questions.
Yeah, no, definitely this is an interesting problem, but people expert in integration probably can understand easily what happens, not me.
Okay, any more questions or comments for Francesco? If not, Francesco, thanks again.
Thank you.
So thank you, everybody. And again, congratulations for Andrei Lichnerovich Prize winners of 2020-2021. And next week, it will be Anna Baliganus speaking on global Poisson. So thank you again, everybody, for taking part in today's event and today's seminar, and see you next week.
Thank you. Bye-bye.
Bye-bye.